So this is what I see from the student view in Canvas. So what the page I'm talking about is over here. Click Pages, and it's the only one, but Reactors and Aspen. So a lot of this stuff is a little familiar. The first 3 videos is from our from Learn Chemie. It's just a kind of high level. Here's the reactors, and if you have this circumstance, you should use this one rather than this one. That kind of thing. Like this first one is 2 minutes long. These others are 4 or 5 minutes long. But just an example problem, and then one with chlorobenzene. Right here is where this video is going to go, and here's an example that I have with ammonia. Ammonia synthesis using Aspen. But really quick right here, some of you have heard me say in 165 or another class that there are 7 reactors that you have in the continuous operation within Aspen. Those are the yield, the stoic, the equil, Gibbs, CSTR, plug, and batch. Now, these 4, equil, Gibbs, stoic, and yield, they're not rigorous reactors. In other words, if you had to size an actual reactor of practical importance that you would build, you do not want to use one of these 4 reactors. These 2, yield and stoic, these are balance-based. So it's just going to make sure that the mass balance works in and out. And you can specify the yield and that kind of stuff, and we'll go over that. These equilibrium ones, equil and Gibbs, all it's going to do is basically minimize Gibbs free energy and give you a result. Sometimes it's completely incorrect, but it shows you what is thermodynamically possible, is another way to look at these equilibrium-based ones. If you have a specific expression, you could use that. But most likely, like with Gibbs, you're just going to put some stuff in and hope it works out. And because it's Gibbs energy, it's going to work out, but you have to know enough about the process, enough about the chemistry and the kinetics to know if it's incorrect or if it's going to lead you down a better, some good path. So these other ones, CSTR, plug, and batch, these are sometimes called rigorous models. Just like your rad-frac column in 160B, these are rigorous models because they actually consider the geometry that you are trying to solve for. So spatial as well as temporal considerations are necessary in these. So they're kinetic-based or rate-based. So what you would typically have with the kinetics that you put in are power law or LHHW. So power law is like the Arrhenius expression. You have an activation energy, pre-exponential constant, that kind of stuff. This Langmuir, excuse me, LHHW is Langmuir, Hinshelwood, Haugen-Watson kinetics. That is going to be something that brings in a lot of catalysis, or where you need to consider the catalysis rather than have this big kind of hand-wavy expression from Arrhenius that says, trust me, this is what's going to happen as a function of temperature. So LHHW, that is where you can put in adsorption and desorption. You can put in different driving forces. It can get pretty complicated pretty quickly, as some of you know from your senior projects. But yeah, so the 7 reactors, and this these 3 points here are taken from this this reference. So if you want to check out some more from this organization or the university, go ahead and click on that link. But right now, I'm going to open up the example. So this example is taking a while, is what it's doing. Anyway, if you were to click on that, you're going to get this. So this is just a very simple expression or simplified. So you have nitrogen and hydrogen synthesizing ammonia. The process itself is incredibly energy intensive, and all of this other stuff, everything goes into just this one reactor. So within this reactor, you have this overall reaction, this global reaction. So it can take place between 150, 300 bar, somewhere around 450 C, and then all that. So we're going to take a look at how each of those, not 7, but 6 reactors can handle something like this. We're going to ignore batch for now, just because the others are continuous processes and it's a lot easier to just be introduced to right now. So take a look at a flow of nitrogen and hydrogen at 20 kilomoles an hour going through at 450 C and 200 bar. So those are the reaction conditions. So what I did, whoops, wrong one, is I did that. So really quick, to just kind of minimize time with this, the components, you can see all I did was add hydrogen, nitrogen, and ammonia. The thermo package that I used is SRK, or you can use Peng Robinson as well. You know, any of those kinds of ones with the little modifications they have. All of those are going to be good for this. But before I go into the simulation, any questions so far? Okay. And some of you have kind of had to mess around with these reactors a little bit, but I'm going to show you how all of them kind of work in there. So this is just a duplicator block for those that aren't familiar with it, down under manipulators. It's just anything you put in here on the left-hand side will be duplicated, so you don't have to, so I can check out which one of these 6 reactors is best, or I want to pursue with other simulation. So I don't have to do all 6. I can just change my inlet flow, again, 450 C, 200 bar, 20 kilomoles an hour, and I'm feeding a 3-to-1 ratio of hydrogen to nitrogen based on our stoichiometry here. And then, so again, just mole fraction there, total moles, and then I'm just connecting all of them, or the duplicator, to all 6 of these reactors. And again, we're going to ignore batch right now. So yield and stoich are the top 2. These are the balance methods, equilibrium and Gibbs, of course, the equilibrium ones. And then CSTR and PFR down here are the more rigorous ones that require temporal and spatial considerations. So if we check out what we need in the stoich reactor, very similar to what a basic column would do, we can specify our temperature or pressure or heat duty or vapor fraction, whatever we have. You know, we don't want to overdefine the problem, so we just need to do 2 of those. So our temperature and our pressure, and our reaction. So when you click on new, you know, you have to specify your components coming in and your components coming out. Now I say that you can have a molar extent, or you can have a fractional conversion. By specifying a fractional conversion of 1, I'm just saying I want to convert all the hydrogen or all the nitrogen. So you can specify which one of those you want, whatever basis it is. And it doesn't matter that this negative is here or not, because no matter what number you put here, it'll be negative because it is a reactant. Just like you have negative R sub A for your rate law, that's again the same rationale for the negatives here. So Aspen will do that for you. And then here you see the stoichiometry, and that's it. It will follow the reaction that you put in. Any questions on stoich?
What if you put in an unreasonable fractional conversion, like based on literature? Is it gonna take that into account, or does this just test the thermodynamics?
Yeah, so it's going to use the databases in Aspen to take a look and just see what can happen or how much energy it requires, and to make sure that you balance the masses in and out. So yeah, it'll make sure there's no accumulation and all of that. And you can additionally add all of your heats of reaction too. I'm just keeping it simple right now, but as Dr. Ron was going through the energy equations, all of that is taken into consideration already because of the properties and all the databases. Sorry about that. And then here you can specify additional stuff, heats of reaction, you know, whatever you need to make a more robust model.
Thank you.
So you just exit that one. So going back here, so now take a look at the yield. So the yield, again, we can specify temperature change, pressure, duty, vapor fraction, same as always. And so the yield one here says we are going to basically have, where we want to see what would happen if we were to have 100% conversion to ammonia on a mole basis. And you can also choose mass, of course. This one doesn't allow a lot of heat effects. The rigorous ones definitely do, but not a lot of these simple models. You can see the temperature effect is basically just if you change temperature or what temperature you have. So not that robust. The equilibrium model here. This one, again, you specify operating conditions, temperature, pressure, duty, vapor fraction. And under the reactions tab, you can, let's edit. You get the same kind of interface here with your components. It asks if there's a solid that it should consider. If there is a solid, then other tabs might open up and you have to just talk about how that will affect your equilibrium. You can also choose molar extent or temperature approach, just like a heat exchanger. There's a delta T that you must consider as to how close that's going to be to allow you to solve it, or have a converged solution, putting it in simulation speak. So all this is good. Putting our molar coefficients again based on this reaction. And any questions on the equilibrium reactor? Okay.
Can you go back to the yield reactor?
Yield, yeah.
Okay, so for that one, you just put like just kind of what's coming out, like the products.
Yeah, or if you want to put in terms of conversion of a reactant, you can do that as well.
Oh, okay.
The yield is not that I have like favorite reactors. I mean, I guess I do because I teach 218 as well. But I mean, like this is my least favorite one. Like if I could not use a yield reactor, I will not use a yield reactor. I'll always try to have a kinetic expression or find a kinetic expression so I can use a better model. But sometimes you just want to see what's going to happen. And so you can just check out some quick kinetics with a yield reactor.
Oh, okay.
And then same, of course, with Gibbs, our fourth non-rigorous one. You have temperature and pressure, or you can have heat duty with this one. And then your drop-down menu here, your calculation option, you can do equilibrium only, equilibrium or phase and chemical equilibrium, or you can specify temperature approach. I wish that wouldn't come up. Or duty, temperature. So you can restrict the chemical and focus on the phase equilibrium, whatever you want to do. I'm just calculating both with this. And that's pretty much it. Gibbs is super simple. So Gibbs will consider all components as products. So no matter what you have coming into the stream, basically, no matter what you have going into your Gibbs reactor, whatever is in your components list from your properties, it will consider all of these as potential products, which is, for the most part, that's okay. You usually don't care too much because you will probably not, this year anyway, do any rigorous, too rigorous stuff in here. But you can also define the phases and identify possible products. So I could put NH3 as a product, and then it will just leave unconverted nitrogen and hydrogen. But by default, this one is clicked, so we just have that one reaction, so I'm just going to keep that simple. And really quick here, other tabs that can come up, especially in reactors, is inerts. Does anybody know why you would have to consider an inert? Kind of relates to what Dr. Ron was talking about for the first 15 minutes.
It could potentially absorb heat or from the process.
Yeah, so especially with combustion reactions, if you have coal, which just we'll just call it carbon. If you oxidize that, you have carbon plus oxygen yields CO2. But you usually don't have pure oxygen. You have air. So if you're not considering pollutant formation like nitrogen oxides and that kind of stuff, and you just say, okay, all the nitrogen coming in with the air is inert, you would want to put that here because that will affect your phase and your chemical equilibrium. So just because you have a general reaction, you can say that, okay, I'm going to specify, say, nitrogen in a combustion scenario as inert so that it can still absorb heat or contribute to the heat transfer effects, but I don't care about it for the reaction itself. And then here you have particle size distribution, or PSD. If you have solids like a packed bed reactor, you can put in some sort of distribution of particles. That is a practical method. Typically that's experimentally determined with sieve trays and shakers and some lab stuff. You can also put in utilities for any of these. There are no utilities that are currently in here, but anybody in 165 will know that utilities, of course, are steam, cooling water, any other process fluid that you might have contributing to heat balance. So again, that's also part of the thermal equation or temperature equation that Dr. Ron was showing you at the beginning. Any questions on Gibbs?
Sorry, you already explained temp approach, but I didn't quite understand. Is it the temperature it's approaching from, or the temperature at equilibrium for the temp approach?
It would be basically the temperature difference that would be required for convergence. So the analogy would be with heat transfer or with the heat exchanger, your minimum approach temperature. So basically which is going to be what, about 10 degrees C, maybe 20 degrees Fahrenheit. And so that is the difference in those two streams to allow that unit operation to converge. For this, having 0 as your approach is pretty standard for the reactors because it's going to be governed by the kinetics or, the thermodynamics that are occurring based on the use of the databases.
Okay, thank you.
So next up, we got rigorous reactors now. So CSTR. Again, operating conditions, you can specify same 4. And here you can specify, of course, your phases. You can also specify, actually you need to specify one of these. So reactor volume, how big is that going to be? You can specify the residence time. So if you have your kinetics in terms of residence time, so how long that reaction is going to take inside of some vessel of some unknown volume. And then you can calculate the volume that you need based on the residence times and flow rates and all that kind of stuff. Or, phase volume and just other things that you probably won't have to use, but are certainly there if you have kind of a weird reaction or a weird process. So I just said, 1 hour for this ammonia reaction. And I completely guessed on that number. If you're going to ask why it was 1 hour, I just put in the first key that was closest to my index finger. Now the kinetics on this, as well as the plug flow reactor, as well as the batch reactor, all require a kinetic subroutine. So I'm going to get out of the block menus. I'm going to go down to reactions. So R1 is a power law type model. And when you click, so if I go actually back out to the top, if I say I want to get a new one, you have to call it something, and then you pick the type of kinetics you want to use when you solve for those reactions. General, LHHW, and power law are the most common ones. Actually, I don't know why you'd use general instead of power law, but because general will default to power law. But if you have crystallization, emulsions, free radicals, another one, Ziegler-Nat. So if you have a special type of catalyst, you do Ziegler-Nat. But yeah, power law and LHHW are the two most common ones. I'm going to cancel because I don't want to add one. It'll mess me up. So at the bottom of that problem statement are so if you Google ammonia kinetic reactions or kinetic expressions, you'll get all sorts of opinions on which one's the best. Again, it just depends on the system that you're trying to model. So in my old design textbook, there's this long expression for the usage or the destruction of nitrogen. So it's this big long expression. It's this one times the partial pressures minus this expression times the partial pressure of the products. This is another one that I found that, of course, I didn't cite properly, as well as an equilibrium expression for the production of ammonia. And so putting this one in would actually be a little tough. So I'm going to show you why. So if we'll click on reaction one, look at the input, and you're going to have a kinetic tab. And if you click this box, reaction is reversible, then you get the equilibrium tab too. For now, we're just going to kind of ignore that or not consider it reversible for now. But no matter what form you find kinetics in, this is how Aspen will treat it. So if T naught is specified, then it will use this kinetic factor. So K, your rate constant, is here. I guess it's actually the pre-exponential constant. Because your exponential activation energy is E, you have your reaction order N, or an associated reaction order. And if it's 0, then this expression just goes to 1. T over T naught to the N power, or T over T naught to the 0 power is going to be 1. So then it just cancels out. Now, if T naught is not specified, so it doesn't have to compare one temperature to another, then it'll use this bottom one, which is basically the Arrhenius expression. So this K here is not the K that you've probably seen in 158. According to the Arrhenius expression, this would actually be A, capital A. So your driving force, for this, again, we have nitrogen and hydrogen, so we have vapor phase. You can pick the basis for the concentration. Now we would have partial pressures. You can pick the units to make sure everything works out, and then you can also have the rate basis be in terms of catalyst or volume. If you have a packed bed reactor, as ammonia production is typically done, actually through a moving bed or a series of packed beds, you pick catalyst weight, because back here, you can see that the K over here is moles per pound per hour. So back here, we have moles per pound per hour for our reaction rate units. So that matches up, or we could have it in metric or whatever. And then, sometimes you just need at least one of these exponents to make sure that the partial pressures know what they're doing and what their job is. Because again, you have 3 to, oh, actually, so I use the larger form. So let's change that. Any questions on putting the kinetics in?
The concentration exponents are from the kinetic reaction equation that you got?
Yes, so that could be, so for something like this, where it's using the half and the 1.5 to produce a basis of 1 mole of product, then I change it back to the 0.5, the 1.5, and so on. So that's actually why this is pretty tough, or you'd have to split it up into 2 reactions, a forward and a reverse. So if this is reversible, you can put in an equilibrium expression if you have it. And if not, what you'd have to do is put in 2 reactions. So you have 3H2 plus N2 yields 2 ammonia molecular moles, and then put in the reverse. So 2 ammonia moles yields in reverse 3H2 plus 1 N2. And then you'd put in this one because you are consuming the ammonia. So just be really careful on the kinetic expressions that you use, because these have assumed forms, as you can see here, like this one explicitly tells you. And anything that is that important, Aspen is going to tell you, or any process simulator should let you know, like, hey, this is the equation we're going to use for this. Did that answer your question?
Yes.
Okay. So the kinetics tab from the chat is within the reactions hierarchy over here on the left. If you have your CSTR, you will have the kinetics tab here. Other ones do as well. Or I guess they have reactions, not kinetics. Yeah. So the rigorous models will have kinetic expressions. The non-rigorous ones will have reaction tabs, where it just says, hey, what are the reactions that you're concerned about or that you want to investigate? So then, let's go back to here. So I actually put in a different one than the one that we just kind of made, because here we have this equilibrium expression. And I wanted to see how that compared to the regular equilibrium reactor model that Aspen uses, as well as the Gibbs one.
Hey, David, can I ask a question here?
Yeah.
So the other ones, for example, the Gibbs, so those are reaction models, right? Meaning they are not reactors, are they? I mean,
correct.
It tells you whether the reaction will happen or not, how much will it get converted, and so on and so forth, or what's the temperature change, or something like that. Or is it like a batch reactor?
Sort of. I mean, like, so yeah, these 4, the Stoic, the Yield, Equilibrium, and Gibbs, these are all thermodynamically dependent, and they're not really going to change no matter what you put in. It'll just be a function of temperature and pressure. Whereas you can tweak the kinetics in the rigorous models, the CSTR, the PFR, and the batch.
So what about the stoichiometric one? Is that a batch reactor? Because unless you have the kinetics, how will you know how long it's going to take or what's the volume?
So with that one, it doesn't actually give you a lot of information. For the Stoic, you'd actually, I mean, because if you wanted to know the spatial limitations or the time limitations or the temporal limitations, you'd have to use a plug flow or CSTR.
Okay.
For a continuous system.
Uh-huh.
So, and then, so when we run it in a sec, then you'll see
Okay, got it. Okay.
Yeah.
I'll
Yeah, so then all of these will actually have a different value or similar, depending on which one it is. So in this in the CSTR, I actually have this reaction too. So I don't have the kinetics active, but what I do have is an equilibrium. So here under the reaction class, I didn't pick Langley-Hinshelwood, I didn't pick power law, I picked equilibrium.
Oh, I see.
So with this one, I say, okay, if I continue to feed stuff, what's going to come out? And so I put in this equilibrium expression.
Uh-huh.
And again, this big K, so K equilibrium is related to the Gibbs free energy, or the change in Gibbs energy of the
Right.
system. But I'm telling it an explicit equation to use instead of allowing the database thermo to take over and tell me what's going to happen.
Okay.
And that was in terms of partial pressures, and you can change it for mass fraction or whatever. But yeah, so we have partial pressures in. Any questions before I run the system?
What if your equilibrium law doesn't like follow the expression it has?
That is a very good question because that trips up a lot of people. If it's in another form, but you still have an equilibrium expression, you have to put it into this form.
Oh, okay.
And so that would be, and so what I've done is actually taken a different type of expression and forced it into this one from, or using Excel. So I just put like temperature from 300K to 600K, change it by 5 as you go down each row, and basically come up with a best fit equation, or a best fit model. Yeah. Additionally, you can use polymath. If anybody's familiar with that, the regression component or the regression settings in there can put it in this form for you, given another expression. Definitely good question, Alex. Anybody else?
Could you click on the first reactor again? There was a heat or thermo tab.
On Stoic?
Yeah. And I didn't quite understand what was going on there.
This heat of reaction?
Yeah, so it's just based off of the chemistry that's going on. Are we inputting stuff right here, or?
So we could. So we actually have the heat of reaction. So we're liberating 92 kilojoules per mole. And so we could put that in here if we wanted to. I ignored that actually. And so I just let the databases take over from Aspen, but we could put that in here. Well, let's run it first, see what it does, and then we can come back and do it.
Gotcha. And then that's just going to affect, the temperature of the stream coming out or something?
Yeah, it'll have some sort of heat duty associated with that per unit of whatever our component of concern is.
Gotcha. Okay, and then I kind of had a second question.
Yeah.
For the rigorous columns, can we put utilities on them?
Yeah, you should be able to. Yep.
Oh, cool.
Okay. Utilities and catalyst. Yeah, so with catalyst, you can say, all right, catalyst is present. So like if you have a packed bed reactor, what you'd actually do, let me go to the proper one, PFR. So if you were to model a packed bed, like so we choose PFR, I do have a catalyst. My catalyst loading is 100 kilograms. My bed voidage 50%. And then from there, you can also determine what your particle size distribution is, or you can just let it do its own thing. You can also click to ignore the catalyst volume in your rate time calculations. So there are other things that can complicate it very quickly. And by checking one box, another tab will pop up or something like that too. But I'm going to keep it simple because in a real system, you do have catalyst, and that's this big one that I'm going to show you afterward.
Gotcha. Thank
Cool.
you.
So reset, because I don't know what I did. Hopefully I didn't change anything. So we run it, and so we have a warning with our yield reactor. Let's check that out. Specified yield has been normalized. Okay, so it doesn't prevent us from having a solution. All it's telling us is like, hey, you didn't specify something, so we had to do it for you. So it's just, you know, hitting us in the back of the head and like, don't be stupid next time. So then, one thing when you have this duplicator and you have 6 reactors, like I don't know what I'm looking at, or I don't want to click on each of these streams. What you can do is if you go up to Home, Stream Summary, you can, oops, hold up. Let me close all this stuff. If you click on the drop down and you just want to look at the products, because all of the inlet streams are all the same. So you just want to look at all the products coming out. Assuming that you didn't click on one. There we go, products. So now we have the product streams for all the reactors. And say you want this out on the flow sheet, so you don't have to come back here every time. You can send to flow sheet. So whatever the current setup is, you can send to the flow sheet. Oh, so over here, I got, I don't want to synchronize the template because I don't want to mess anything up. But yeah, we'll call it that. So here, every time I solve it, it'll just update. So coming in, so my mole flows, so I can see that if we have 20 coming into each reactor, the only reactor that doesn't have a reaction is actually PFR. So something's up with those kinetics, but I get a reaction for the stoic, for the yield, for the equilibrium, and there's just no liquid coming out of the equilibrium. So that's why this is 0. Gibbs is also a reaction is occurring as well as in the CSTR. So now if we want to take a kind of a closer look at those, go into our streams. Again, all of our product streams are here. Let's take a look at mole fractions. So if we zero in on ammonia, we can see that, I wish I could, I don't care about any of these. Not all of them. That's all right. Sorry, I'm gonna have to scroll up and down. So we have complete conversion in our stoichiometry or stoichiometric reactor and our yield reactor. We have 27% conversion in our equilibrium and our Gibbs reactor. So 3G and 4B, Gibbs and equilibrium, we have 27% conversion. And we have 99.9% in our CSTR based on our equilibrium expression. So just because it's equilibrium, it's still different than what the thermal package would specify. And something's up with our kinetic expression, so the PFR didn't solve. And troubleshooting that, as you know, troubleshooting other stuff with Aspen can take a while. So I'm not going to take up your time right now to figure out what I changed when I was going through the system. But does anybody know, or so how practical are these results? Does anybody know what a single pass through on an ammonia reactor would be in industry?
Very low.
How low is very low? Is it lower than all of these?
15 to 25%.
Yeah. I was actually going to say 21%. So, yep, that's right in there. A single pass through an ammonia reactor, that's why you have to recycle it at 7 or 8 times at least. Each kind of fluid element as it goes through, you have to recycle it that many times. So surprisingly, the Gibbs and the equilibrium are the closest to what you would expect. But again, that's very temperature dependent. as well as pressure dependent because of the partial pressures of the system. So in this, the stoichiometric reactor and the yield reactor are not good to use. And again, you would know that by doing just a little bit of literature review to see what you can expect to know if you're headed on the right track. So if we change that really quick in our gives, if we change that to 300 bar, say 300C. I know we'll keep 200. We only want to change one thing at a time. We reset. Oh, when's this class over?
It's 5:45, so you have time.
Okay. So we run this. So now, if we go, oops. What? No. All right.
Did it
That
crash?
Aspen file just crashed on me. Man. Huh.
Did you save?
Classic Aspen.
Don't you love Aspen when it crashes on you?
Yep, I know everybody's had that similar experience. Anyway, by doing that, our 27% conversion to, or 0.27 moles of ammonia, by dropping that, we would have actually made more ammonia, over 50% conversion. So that is actually incorrect. So it's very dependent on the, dependent on those, on the temperature and pressure. Huh. That sucks. Let me see if it auto-saved it. Yeah, restore. Okay, run. I think you're trying to do too much at one time. Okay, there we go. So the same issue with the yield reactor, but again, it's just a warning telling us, hey, we did something because you didn't, so everything's still good. Take a look at our streams. And yeah, so almost 70% conversion when we drop the temperature from 450 to 300. So again, looking at the temperature for the equilibrium reactor and the Gibbs reactor. So that's all I changed. And our conversion went from 27% to almost 70%. So there's a lot of issues with this when you're trying to solve for a real system. If you're just trying to see what's possible and what the thermodynamics is going to govern for you, Gibbs is a good one to use. It's easy. If you have a specific set of reactions, I personally would recommend the Stoich. But again, whatever works best for you is the one that you should use. So really quick to see how complicated, or any questions on this before we see how complicated it can get?
So I guess, do you advise just running all of them just to see which ones will give us reasonable results first?
If you have a set of reactions, yeah, it does not hurt to run the Stoich, because what you'll do is you'll pick a rigorous reactor like a PFR, okay, adiabatic, or maybe a reactor with a specified temperature. So we want to specify constant reactor temperature of 200. No, it was 450. The configuration, so this is where you're going to have an issue. And this is where it's good to know what the design equations are behind Aspen. And that is where you'll pull a lot of information from 158, because it's a little tough to find some of those governing equations that make Aspen run like it does. I'll show you a couple places you can look, but you know that a CSTR is just it's basically a set of linear equations, and you can solve for those. You can do that by hand. Solving a differential equation in terms of plug flow reactor or PBR, that's what it's doing behind the scenes. And again, it is geometry dependent or temporally dependent if you pick the residence time option for CSTR. Yeah, so we could also, actually, let's drop this down to 0.1 hours and see if we get the same kind of conversion. And we also changed something in the PFR. Oh yeah, so a specified temperature 450. I don't think it's going to help. Something else might be up with the kinetics. Take a look at our streams. And mole fractions. So the reaction does happen pretty quickly. This changed a little bit, but it was at the 4th decimal point for the CSTR. When we went from 1 hour down to 0.1 hour, or 60 minutes down to 6 minutes. And something's up with the PFR. But that is how you would go in and add the reactions. Power law, LHHW, equilibrium are the most common ones. I'd be surprised if you used many others. But really quick, some resources for that. Again, there are some people in here that are not in 165. So feel free to email me. I have plenty of resources, or I can add you to our 165 course, and you can actually see other Aspen stuff as well. But if you click on examples here, you have all these examples you can pull from. So energy, well, not energy, carbon capture. So if we want to look at amines with ammonia, do not close current one. We can open up that and we can troubleshoot a lot of issues, or just see how somebody else did something with an absorber and a stripper. So here we have, it's on a reacting system. So why did I choose this one? Sorry. Oh, let me just show you the actual ammonia one. So this is found in the examples, resources, examples. So all of this upstream stuff is just to produce the CO and the hydrogen necessary to actually make this single little block work, synthesis. Everything else is for recycle and refrigeration to condense out the ammonia from the product stream. So if we click on this synthesis block, it's actually a subroutine that flows in. There we go. Clean this up a little bit. So it comes in, goes through this splitter, and part of it goes to this plug flow reactor. That is then routed into a heat exchanger, goes through a plug flow reactor, heat exchanger, PFR, heat exchanger, PFR, and then out. The split stream runs the other direction through these heat exchangers. And what this does is, this is a heat management technique called cold shots. Because the exit of these four plug flow reactors is a little too, I think, warm. And what these heat exchangers do is it cools it down to manage the exothermic nature of the reaction, so then it can keep everything in check and you don't get runaway reactions. So this is a practical way of employing the temperature equation that Dr. Ron was talking about at the beginning, as I think last class too. And so, yeah, this is actually done in one physical reactor. If you were to look at a synthesis reactor for ammonia, it's one unit. It's not 7 units. It's not 3 exchangers and 4 reactors, because it will run through, it's all geometry dependent again, but this is just letting it solve for the kinetics. So the reactions here are actually complex. So we can click on these and see that we have ionic forms, but we have kinetics and equilibrium. In here we have all of the kinetic expressions, some equilibrium expressions here for the specific reactions. In the drop-down menu, you have other ones. You have all of these. So yeah, it can get pretty complicated pretty quick. But I mean, don't forget about all of these examples here. And each of these does have an associated, you can't see it, man. There's a PDF that goes along with each of these examples. You can access it through desktop.sjcu.edu. If you click on the desktop version and sign in through a virtual 333 machine, you can access the PDFs this way. If you're using Citrix, I'm afraid that you can't. There's no way to do that. However, because you're not actually working on a physical drive. But if you need the associated PDF of this, let me know and I can send it to you. Some other really good ones, of course, there's the help, but under training, if I type in reactors, getting started with Aspen plus reactor models. If I click the little play button, so a window pops up, and I think I can.
Welcome to the Aspen Plus teacher.
So it has basically
This video will introduce
little videos for chemistry, temperature. It starts automatically playing.
the reactor tab of the model tab.
Yeah, so here's what I was talking about with the equilibrium-based, shortcut or balance-based, and then the rigorous or the rate-based. Different models, how you can start to model those as well. That's kind of it. That ended very uneventfully. Any questions?
So that, no, go ahead.
Oh, okay. Thanks, Evan. So how would we know how many PFRs to draw in for Aspen?
You could get away with 1 for the most part if you have a large industrial scale process. And when I say large, I mean like tens of tons per day or something like that. Well, I guess depending on the heat transfer. You can, let me see if I can do it on this. So you're going to give me, yep, temperature versus reactor length. So you can use something like this. So all I did was went under, nope, wrong one. So if I'm under my reactor setup, up here I get the plot menus under the home ribbon. And so I clicked on the temperature one. And so you will have thermal limitations on an industry or on a practical level that will limit how far you can go. So if you have 4 3.6 meter long reactors, and so maybe the wall thickness allows you to go to 400, say 500 degrees C, you have a factor of safety, so you don't want to go over 450 or something like that. Then you can you can say, okay, I'm not going to go over 450. So if they're 3.6 meters long, you start to limit what is practical because of the material considerations and everything else. But that's plant design, so we'll try I won't delve too much into that because many of you in that class even don't care. So it's cool. I understand. But with the temperature plot here, or pressure or something else, you can start to see what's going on. So we select all of these, going down the molar flows. So it could be that we just reach conversion, so we can cut it short, something like that. So to directly answer your question, Chichwar, you will have some other limitation that is either assumed or imposed to limit the number of reactors.
Okay.
If you start to restrict the geometry as well.
Okay, thank you.
And that's actually part of the problem with a lot of this stuff, is that there are so many knobs you can turn, so many things you can decide or not decide, that yeah, it is daunting pretty quickly. But if you just kind of take it one little, just kind of one operation at a time, then it's more manageable. Evan, did you have a question too?
Yeah, mine was about the PFRs in series with the heat exchangers. Was that's to simulate multiple passes? If we need multiple passes through a reactor, we would do something like this instead of doing like a recycle stream?
Yeah, because you can do a recycle stream. Let me show you real quick. Ammonia. So what an ammonia synthesis reactor actually looks like is something like this. So you have particle beds and in purple, and you have open paths for vapor or products and reactants to go up and down and zigzag inside the reactor. So this is kind of like a spiral reactor. You could also have different catalyst beds here as you go up and down the column. And so if this is, so if these are highly exothermic reactions inside these beds, you have cold shots. So your cold feed relative to the reactor, you can have one coming down, go through bed one, you have your second feed going through bed two and all that, and that helps you manage all of the heat that's being generated in the reactor. Alternatively, you can have what's hot shots. So if this is an endothermic process going through this bed, and you put in a hot feed to keep the temperature up, to keep conversion higher, selectivity, or whatever your specific thing you're looking at is, then you can keep the bed warm by putting in warm reactants to get some okay products. And then it just goes through the bed like that.
Thank you.
Or you could have just actual, just a straight up heat exchanger on the outside that's zigzagging back and forth in and out of the reactor. So this is the system here on the left that this is trying to approximate. So again, Aspen doesn't necessarily need to reflect reality. You can utilize Aspen however you need to solve the system as it makes sense to you, or as is given to you from some problem statement or future engineering firm or whatever. And the really quick, the best explanation of that I can think of is actually the coal gasification model. What? I spelled it right. There we go. So this entrained flow gasification model, it uses different reactor types to approximate a single high temperature, high pressure reaction zone. So you have coal coming in this case, as well as oxygen. Now, in the physical system, they're coming in the same port. But here you have the combustion reactions being taken care of. Here you have endothermic pyrolysis reactions being taken care of in a, what block is that? Equilibrium, I think. Oh, a yield reactor. So a yield reactor is taking care of your pyrolysis reaction, your endothermic stuff. And then all of that is being fed to basically, so this column, this is actually allows you to separate the ash versus what's going to burn. And all of these dotted lines are the heat flows going back and forth to share the heat that is being produced or that is required from another block. So 1, 2, 3, 4, 5 reactors and 1 column are used to approximate high temperature, high pressure reacting flow inside of a reactor. So yeah, because if you were to draw the block flow diagram of this, you'd have coal plus oxygen going to product. But all of this is used inside to try to manage all those reactions and everything. And it does actually a pretty good job. Because this is what I used a long time ago to model up a pilot scale gasification system.
Can you add valves in Aspen?
Yeah. So we go back to a simpler one. You can add pressure changers, and a valve is going to do that for you. So you can put in your flow coefficients. Again, these are control valves. So you have the valve body where you have the plunger or the needle going up and down, and then you have the big part on top, the diaphragm, or the actuator that is moving everything up and down and actually controlling everything. So, so again, by valve, this is a control valve, or you can have it approximate a valve that happens to have just a high flow coefficient. So yeah, then you just kind of put in your outlet pressure that you need, making sure that the pressure drop through there is manageable or expected, you know, whatever you kind of need to phrase it as. Any other questions? And for those of you in 165B next semester, you're going to get a lot more of this the first 2 weeks. Just a kind of a heads up.
Can I ask another question? Sorry,
Sure.
It's more my senior project, but so since no one else is asking questions right now, but because we have adsorption and desorption, so how do we separate like the loading and unloading? Like how would we see that in Aspen?
You would need to use the dynamic mode that allows it to be basically flowing through as a function of time. That, in my opinion, is well, anybody's opinion probably is beyond the scope of this class. So what I would recommend in order to complete a mass balance like that is to model one at a time. Look at the desorption and then look at the adsorption separately. Because then you can put a time function to that. And then you can say, okay, if adsorption takes 30 minutes, desorption takes 25 minutes. So then you're on a 30-minute cycle as opposed to a 25-minute cycle if you're going back and forth with those.
I see. Thank you.
And for anybody that's curious, adsorption and desorption kinetics can be taken care of within Aspen using Langmuir, Hinchelwood, Haugen-Watson kinetics. If that didn't make sense, it's cool. But if you click a new reactor type, you go LHHW, so Langmuir, Hinchelwood. Oh man, okay. Let me just make up something.
Oh, they did learn Langmuir Hinchelwood, so.
Okay. Yeah, so with that, you have this here. So this updated from the Arrhenius expression. So the Langmuir Hinchelwood kinetic expression is your kinetic driving or your kinetic factor times your driving force over your adsorption expression. And this is a big equation, most likely, with a bunch of big K or capital K values or equilibrium expressions. And the way you do that is you can put in adsorption, and this is complex, and I'm actually trying to help senior team with this now. But there are certain coefficients that you need in order to make this work. And these coefficients are basically going to be the K factors in front of your partial pressures in this denominator. Your driving force, of course, is just going to be probably the partial pressures. So your whatever. Yeah. Your partial pressure is going through the system. Oh, that's why it didn't work, because this is not vapor. There. So now you can do partial pressures as long as you have your reactant phase being vapor. And then you can put your coefficients in. Again, it's going to be of a specific form. And oh yeah, the solids went away when we clicked vapor. So yeah, it can get pretty complicated pretty quickly. But once you, I mean, so understanding the chemistry, as many of you heard me say before, is the most important part of any process. Because from the chemistry comes all of the kinetics, and then the reactors set up, and then the separations, and then the heat management after that. Any other questions?
No, you said you didn't really, or you preferred like the later two reactions because they take into account like the size and some of the heat duties of the reaction.
If you're trying to model a physical system, yes, then you need a rigorous reactor. So CSTR plug or batch. You can see that these four, Stoic, Yield, Equilibrium, and Gibbs, they don't say anything about the size of the reactor or how long it will take. I mean, you can have an equilibrium reaction, calculate in a tenth of a second in Aspen, but the physical system for equilibrium could take a couple of years to reach, or it could take a couple of years to reach equilibrium in an actual system under, of course, obviously non-ideal temperature and pressure. So yeah, this Equilibrium and Gibbs, they don't tell you anything about how long it'll take. We'll tell you the heat duty on all of these though, if you click on the results. Oh, we changed that one, or that's not even one, Gibbs. Yes, you can get heat duty from all of these as well.
Okay, and then also like hypothetically speaking, if we have a memo due that requires like material balances, would it be fine to use like the first couple reactors because they do balance like the mass and the moles going into it?
Yes. Yeah, you can use Stoic or yeah, you can use these other ones in order to complete that balance. Because then you would have to modify, or you'd have to actually come up with a good design for a reactor, which we haven't talked about in 165, and Anna, have you talked about how to size reactors?
Yes.
Okay. Oh yeah. Then Alex, for your memo too. Yeah.
All right.
No, I'm just kidding. But yeah, you can use a stoic reactor to go after those general reactions, or the overall reactions we have. And I will upload this to the 158 canvas. Think. Anand, is it okay if I put it in other readings?
Oh yeah, certainly. Yeah. Mhm.
Okay. So I'll put the file in other readings, but I'll also put a shortcut to it in pages. So you only have to go to this to find everything we discussed today.
Sorry, a little off topic, but in the heat exchanger tab, there's a type of valve. I'm not sure if it's different than that type of valve. Or
which reactor?
it's actually the ribbon all the way in the bottom, the heat exchanger tab.
Oh, heat exchanger.
If you click to the left, I think.
Click which one?
The drop down menu for the heat-X. So the heater, sorry. That top right, or all these valves too.
Whoops. Never had to use one of these. Flash type. Oh, I think this is if you have a quick condenser, or it's a throat. You're putting a bunch of fluid through like a Venturi meter or something like that, and it's condensing or heating up or something like that. So it's exchanging heat by changing the physical properties of the stream.
Okay, so they're very different.
Yeah, so not a valve. This would actually be that'd be pressure changers. Yeah. I guess you have that as well. Oh. No, never mind. This one's a valve. But yeah, exchangers here. This is going to be if you quickly condense something or basically subcool it, as you can see here, or if you superheat it too.
Thank you.
Yep. Anybody else have any questions?
Do you think this would be relevant even if your advisor absolutely hates Aspen?
So yeah, if your advisor for senior projects does not like Aspen, they can't tell you not to use it.
Does this work for biological reactions as well? Or?
Yeah. So really quickly, then you can go up to components, and it does have some bio stuff in the component list. You could also specify your own component. There's a way to do that.
There are some very niche things in there, but at the same time, there's not everything. Like if you have like agar and a broth or something, they don't have that, so you have to specify it yourself. I've been running into that issue. Well, I kind of neglected it because it was super tiny, but that's just in my case.
Yeah, but there are some things in there that you can put yourself having like binary diffusion coefficients and that kind of stuff. That is a little bit of a headache depending on the method that you pick. So like NC prop is non-conventional properties. When you choose your own, or when you specify your own component, you have to put in what some of the properties are so that everything else works out as far as the calculations go. Those are most often enthalpy and density. density to make sure that the mass will work out, and enthalpy to make sure the energy balance will work out. There might be some other ones depending on what you have, but then you could also, that you could actually kind of shortcut it that way by putting in your own and specifying the bare minimum you need to. Do not complicate it, I recommend not complicating like that. And then if you have kinetic expressions for a biological reaction, you can then just put those kinetics in and tell it, all right, this thing that I specified is going to react like this. And then Aspen's like, okay, if that's what the math says, then that's what I'm going to do. And then it'll carry out that that unit operation. If you want to check anything, you know, in Aspen that you have to do in Excel or something like that for your advisor as well. Cool. Any other questions? You've had to see me twice today, so I'm sure you want to get rid of me.
Well, I'm sure we'll have more questions for my project.
No, I'm sure everybody will.
I have a quick question about bioreactors.
Sure.
So as you know, my project's also involving bioreactors, and I was having issues with trying to get a chemical equation down, like a stoichiometric ratio down, due to the fact that we have a bacteria host as our, or a yeast host as our growth medium, and I'm really not sure how to approach it if I have like a host in the system.
You can.
I've tried asking.
So yeah, so to balance that big reaction is kind of tough because you have a lot of carbon, hydrogen, oxygen, nitrogen, and because it's just some biomass, or not biomass, like I think it is, but some cells that you have. SuperPro does do a lot better with biological reactions. And SuperPro is available on the desktop servers.
Oh, awesome! I've gotten the rest of the stuff balanced out in Aspen, as in like all the post production processing is all done in Aspen, and I was just wondering if I could shove the production of the chemical itself in Aspen to save me some time and some headaches.
It depends on how big of a headache you want. You could also just see if something's doable within SuperPro, or what you could expect, and then you could just kind of you could join the two in Excel for a big mass energy balance.
All right. Cool. All right. Thank you.